Okay, MVT, and extremes. This video here is going to be where we start talking about how to graph functions given derivatives, both first derivatives and second derivatives. So mean value theorem, both of these are very, very important lessons. So let's go ahead and get started. So mean value theorem is an existence theorem. So if, and this is so very important, if f of x is continuous. Now, with this too, they don't always tell you it's continuous. What they'll do is they tell you that it's differentiable. And we all know that if a function is differentiable, then we can also conclude that it is continuous. If a function is continuous at every point on a closed interval and differentiable at every point of its interior, then there is at least one point between a and b at which the derivative at c is equal to f of b minus f of a all over b minus a. Now, let me break this apart. First thing, this right here is super important. This value has to occur between a and b. It cannot be at a or b. This is a multiple choice question right here. And what they're going to do is one of the options is going to include the endpoints. This only ensures that it exists between the endpoints, not at the endpoints. So just watch that. Now, let me draw what this theorem is saying. So you have a function. Let's say it looks like this. The first thing you do is you draw a secant line that connects those endpoints together. Well, I should say the first thing that you do is you ask yourself, is that continuous and differentiable, which it is. So if you look there, it's a continuous differentiable function. Now, between those 2 points, I connect that and I find the slope of that line. That corresponds to that part of the equation here. So what this is saying, what mean value theorem says, is that there's another point, at least one, between those endpoints. Yeah, I did not find it because as you can see, that's not parallel. It would have probably been a little bit higher up. There it is. Where those 2 lines would be parallel. Because remember, this is a slope is equal to a slope. And when 2 slopes are equal, it means that they are parallel. Okay, so all you're doing is you're going to connect the 2 endpoints together and you're going to find the slope of that line. And then you're going to find a point where the slope of the tangent line is parallel to the slope of that secant line. Okay, so slope of tangent equals the slope of the secant line. Slope of tangent equals slope of secant, or they are parallel. Okay, so here's an example. So it's a really simple one. We've got a y equals x squared graph. So there it is, looks just like that. It does satisfy the hypothesis of the mean value theorem because it is continuous and it's differentiable. And we are only going to go between 0 and 2. Oh my gosh, sorry. There we go. So between 0 and 2, something like that, then find the solution to the equation. So basically, again, what I'm going to do is I am going to connect my endpoints together. I'm going to find the slope of that line right there. I'm going to call that M2 because it's kind of the second side of the equation. And then I need to find a place somewhere in between here where the slope of that secant line, I'm going to call that M1, where they are equal. Okay, so 2 things we need to do here. Let's go ahead and just find the slope of that secant line right there that connects that together. So that would be equal to f of, and you just use the endpoints. So I'm going from f of 2 minus f of 0 all over 2 minus 0. So therefore, we have x squared. So I'm going to have 2 squared minus 0 squared all over 2 minus 0, which means I have 4 over 2 which is equal to 2. So somewhere that slope has to be equal to 2, the slope of m1. So now on the other side, you can see that I have a derivative. So I've got x squared as my function. So the derivative would be 2x. So I want where 2x equals 2. So x will be equal to 1. So at x equals 1, the slope of the tangent line there is equal to the slope of the secant line. And notice that 1 is in between that interval. So even though there's square brackets, it could not have happened at 0 and 2. It has to be in between. Okay? So basically, find the slope of the secant line, find the slope of the tangent line by taking the derivative, set them equal, and solve. Okay, now I'm going to skip that. I'm going to come back to that in just a moment. The second thing that we need to talk about today, so mean value theorem. Oh, by the way, I should add in one quick thing. So ignore this really quick. We're going to come back to that in a second. But why do we care about the mean value theorem? Mean value theorem. If I have an endpoint here at 0, and I have another endpoint over here at, let's say, 5, where we use mean value theorem is if you were to connect those points together, that secant line there, the slope of that secant line is equal to 0. So what that guarantees, as long as we know that it is differentiable and continuous, which we know that it is, it means that somewhere there is a slope of 0 for a tangent line. Now, when your slopes of zeros exist for tangent lines, what that guarantees is a turning point, or a maximum, or a minimum. And that's what we're kind of looking for here. Okay, so mean value theorem exists to tell us whether turning points and minimums and maximums occur. So speaking of minimums or maximums, we have two different types. We have absolutes or global maximums, and we have relative or local maximums and minimums. Now, a global max or an absolute max is exactly what it sounds like. It is the absolute highest point or the absolute lowest point. So your absolutes, they can occur, 1, where your derivative equals 0, because that's going to be a turning point. 2, where the derivative does not exist. Or 3, they can occur at endpoints. Okay? For your relative or your local, now these are the ones that actually look like this. Your absolutes, they could be at endpoints. So it could just be the highest point, the highest place that the graph goes, or the lowest place that the graph goes. It doesn't have to have that turning point there. For a relative, you have to see what we would consider a maximum or a minimum. So the graph actually has to turn around and go in an opposite direction. So local would just say, or relative would be 1 where your derivative equals 0, or 2 where your derivative does not exist. And that would be something like an absolute value graph where your derivative does not exist. Critical points. Critical points happen where your derivative equals 0 and where your derivative does not exist. So when you're finding critical points, step 1, take a derivative. They both have to deal with derivatives. Then see if there's a discontinuity or a vertical tangent, something like that. Like if it's a fraction where the denominator would be 0. Or you can, if it's a polynomial, just set it equal to 0. That is a critical point. Critical point is first derivative. So remember that, first derivative. Because in a second, we're going to talk about what the second derivative tells us. Example, find the critical points and label extreme values. Okay, so looking at this graph right here. Well, this is y equals 2x cubed minus 6x minus 5. So with critical points, remember this is first derivative. So I need to find out what y prime is. So that will give me 6x squared minus 6. I'm going to set that equal to 0. Which means I have critical points at x equals plus or minus 1. And if you look here at -1, and at 0, you have where your derivative equals 0. Now, both of those gave us local minimums and maximums. From my last slide, this would be an absolute max, and this would be an absolute min, and these are my local mins and maxes. First derivative test for increasing and decreasing. Remember, derivative equals slope. So if your derivative is positive, then your function is increasing, because if your derivative is positive, it means that your slope is positive, which means your graph is increasing. Okay, same thing for negative. If your derivative is negative, then your slope is negative, which means that your function is decreasing. Where is the function increasing and where is it decreasing? Okay, so the first thing we need to do is we need to find our derivative. So your derivative is 3x squared minus 4, which will give me, set that equal to 0. That does not factor nicely. So I'm going to just add the 4 over. So we would get 4/3 is equal to x squared. So therefore, x will equal plus or minus the square root of 4/3. Now, what I like to do with this is I like to put this on a sign pattern picture. So sign pattern picture. So I put my negative square roots of 4/3. I put my positive square roots of 4/3. 0 would be right in the center of that. So what we're going to do is we're going to plug values into the derivative to see if they're positive or negative. So remember, if your derivative is positive, then that means your graph is increasing. So I'm going to find f prime of 0, because that would be right there in that middle section. F prime of 0. So you go to your derivative. So my derivative is 3x squared minus 4. And I don't care what it is. I just know that it's going to be negative. So in between there, it's negative. Now I'm also going to test on either side of that. I don't know exactly what that value is. So I'm going to use f of negative 10 and f of positive 10. So 3 times negative 10 squared minus 4 will give me a positive number. And the same thing for f prime of 10. Be positive on either side. So to answer this question, where are we increasing, where are we decreasing? We will be increasing from negative infinity to negative radical 4/3, unioned with positive radical 4/3 to infinity. And we will be decreasing from negative radical 4/3 to positive radical 4/3. And that's all underneath that radical there. Sorry for that handwriting. Okay, now the last thing I wanted to do is to label any local extremes. Now think about this right here. So at negative 4/3, your function goes from increasing to decreasing. I increase, then when I get to there, I decrease. That means that this would be a maximum. And then here, that would be relative. We don't know if it's not, because it's an x cubed, so we know end behavior goes down forever and up forever. And then at positive radical 4/3, our derivative goes from decreasing, or negative to positive, which means our graph, our function, goes from decreasing to increasing. So therefore, you have a minimum. Okay, so do a sign pattern picture using your critical values, your critical points, and then test points on either side to see what your graph is doing. And last but not least, our second derivative test for concavity. The second derivative test for concavity is the same thing that we just did, only we're going to have concave up where your second derivative is positive and concave down when your second derivative is negative. Okay, so concave up looks like a cup. Concave down looks like a frown. So if we didn't have concavity, all of your graphs would be straight lines. Okay, because of concavity, our graphs aren't straight lines. They're normally curved like that. So this would be an example of a concave up, or where the second derivative is always positive. Now look at an x cubed graph. Right here, you're concave down. And right here, you are concave up with a switch right there. What is that switch called? That's called an inflection point, and I'm going to give you that definition in just a minute. So second derivative, when your second derivative is positive, you're concave up. When your second derivative is negative, you are concave down. So use the concavity test to determine the concavity on the interval. Okay, so concavity test is second derivative, but we need the first derivative to get there. So we've got y equals x squared, first derivative, second derivative equals 2. Now, that second derivative is always positive 2. Now, if you think about an x squared graph, its concavity is always 2. It is always concave up. Okay? Now, just for fun, let's throw in y equals x to the third. We already saw this one. So the first derivative is equal to 3x squared. Your second derivative is equal to 6x. Now, like I said, you're going to have a concavity switch when this is equal to 0. So I'm going to set that equal to 0. So at x equals 0, you're going to have a concavity switch. Now, again, I would do a sign pattern picture. Put 0 there in the center. I'm going to test points on either side into the second derivative. So y double prime of negative 10 and y double prime of 10. So if you plug that into here, you're going to get negative, and then you're going to get positive. Which means that you are concave down until 0, and then you're concave up after 0. Okay. And then my last one, I think I have one example left, but points of inflection is where your second derivative equals 0. And this is not true for critical values. And your concavity changes. Very important to note that. You must change from concave up to concave down. If you were to stay like concave up, it is not considered an inflection point. So second derivative equals 0 and your concavity changes. Last slide. So find all points of inflection. So the first thing we need to do is take the first derivative. For this one here, I am going to switch over and use the calculator. So if you remember from class, we've got our calculus thing. So you go to menu, you go to calculus, you go to derivative. This only works on the Inspires, the black calculators, by the way. So if you don't have that, you can type it in for right now, but you're definitely going to want to get one for the exam. So your first derivative is equal to negative 2x e to the negative x squared. And then I'm going to find my second derivative by doing the same thing. So you go to menu, calculus, derivative, and again with respect to x. And that's going to give me 4x squared minus 2 e to the negative x squared. Now, an e graph is never equal to 0, so you can actually ignore all that. So we need to set this equal to 0, but really you just need to set this part here equal to 0. And then when you solve that, hold on one second. You're going to get that x equals plus or minus radical 2 over 2. And those are your points of inflection. And then from there, you can test to see if they are concave up or concave down by doing a sign pattern picture and testing points. Now, I know that that was a lot. So what I did was I also attached a vocab paper. So hopefully, as you went through this, maybe you filled in what some of these things were or how to find them. But just as a quick review, and if you don't want this review, you can stop listening at this point. But absolute extremas, they occur when your derivative equals 0, and they occur at endpoints. And when the derivative does not exist, it's the absolute highest point and the absolute lowest point. Your relative extremas, they must look like a maximum or a minimum. So you take your derivative, set it equals 0, or consider where it does not exist. And like I said, it will look like a maximum or it will look like a minimum. First derivative test, you take the first derivative. That tells you about increasing and decreasing. That can also tell you about where maximums and minimums occur. Second derivative test, this tells you about concavity. So you take the second derivative and then sign pattern picture to figure out if your graph goes from concave up to concave down. Critical point happens when your derivative equals 0, your derivative does not exist. Increasing is when your derivative is positive, decreasing is when your derivative is negative. Inflection point is when your second derivative equals 0. Concave, and it must switch concavity. So that's an important one there. Second derivative equals 0, and you must change concavity. Concave up is when your second derivative is positive. Concave down is when your second derivative is negative. And mean value theorem, circling back around to where we started today, this is when the slope of a tangent line is equal to the slope of a secant line. And it's an existence theorem because it says at some point that slope must exist as long as you are continuous. And remember, it only occurs on the inside of an interval, not at endpoints.